All right, so we were talking the other day about chemical reactions and how they work and different types of reactions. And all of you have had this before, I understand that, but we're going to go over it again a little bit. So we talked about reactions like that come in, if we get the energy from the sun, the sun puts the energy into chemical reactions that make chemicals like glucose. So we have exergonic versus endergonic reactions. An exergonic reaction is when you break the bonds apart, they release energy. When you put energy into the substances, they create bonds. So that's an endergonic reaction. So we have this endergonic reaction where there's energy inside this chemical. It's building up a larger molecule. So if you take glucose, C6H12O6, there's a lot of potential energy in that molecule. When we break it down, it releases energy. That's exergonic. Okay, it breaks it apart. When we put it together, it's anabolic, or what we call endergonic. The energy is used to make that chemical bigger. So most of the chemical reactions in the human body are reversible. A plus B equals AB. So if you had sodium plus chlorine, you get what? Sodium chloride, which is salt, table salt, right? Or you can take sodium chloride, take salt, break it down into sodium and chlorine, so you can use the chlorine in your stomach for hydrochloric acid and the sodium in your nerves to make the electrical impulses in your nerves work, right? The sodium-potassium pump. We can break those down. So chemical equilibrium has to occur in order for this body to work. That keeps us in homeostasis. So we need energy to make substances, and we have substances broken down and releases energy. That's where we get our catabolic reactions that also produce our ATP. It breaks down the chemicals of glucose, makes them into ATP molecules, and that's what we get. Now, certain reactions can be affected by different situations, different environments. If you increase the temperature, you increase the rate of the reaction. It goes faster. If you decrease the particle size gets smaller, the rate gets bigger. So let's say we have this chemical reaction. We're going to use chemicals, but we're going to use marbles. We have two reactions, marbles and bowling balls. Right? If I have a bunch of marbles and I drop them on the floor, they're going to spread out really fast. But if I have a bunch of bowling balls, they hit the floor, they're just going to kind of slow down and stop. They're not going to go very far. Right? So the smaller the particles, the faster they go. If you have someone that walks in the door, they have lots of perfume on, that will quickly, those little molecules will travel throughout the room. If it's really cold, it takes longer than if it's warm in that room to do so. Okay? So we increase the concentration. The more perfume that's on that person, the faster that's going to expand. The chemicals are going to travel farther and quicker, and you're going to smell them faster. Hopefully it's a good smell. Right? There's a guy on the internet that he's talking about someone at a store, and every time he smells them, he goes like this. He's talking to his wife, and it creates an image in his brain that he can't tolerate. It makes him want to throw up. So those things can happen. Catalysts are chemicals that enter into a reaction. They increase the rate of the reaction, but they really don't affect the reaction that much. They're like enzymes. Enzymes and catalysts work about the same. They increase the rate by changing the mechanisms. And sometimes we get some chemical reactions like this where things just kind of go off, right? Nobody even laughed. Okay, so why is water essential for life? Let's talk a little bit about water. A little discussion here. Hydrates the body. What's that? You saw it? Probably right. I just didn't hear you. I'm sorry.
We're just like, our body's like, what, 75% water?
Very close, 70%. When you're a kid, we're probably not quite so much anymore. So I definitely am not. You may be, but I'm not.
It's good at absorbing heat.
Good absorbing heat. Okay. What else does water do for us?
Protects us.
What?
Protects us.
Protects us. How? I don't know. Makes us kind of squishy? Yeah, sometimes that's true. How else can water be effective in the human body?
It's a cleaning mechanism.
Cleaning mechanism. How does it clean us up?
Doesn't it pass through and it clears out the toxins and stuff?
Right. Cleans out the toxins through what organ? Kidney. Kidney. Somewhat the liver too, if we especially helps move the bowels through, right? Moves the feces through. Okay, so how long can we live without water? 2 days, 3 days? I think I hear people saying. Anybody say 4, 4, 4, 5, 5, 5? Anybody want to go 5?
I think it's 3 to 5.
3 to 5. There we go. That's more like it. 3 to 5 days. Now, what's that big? There's a big spread there. 3 days to 5 days is a long time, right? Why is there a spread there?
Depends on how much water is already in your system.
Exactly. How much water do you have in your system now? And also, what is the temperature? Are you going to be sweating a lot? Or are you going to be working a lot? Makes a big difference. You go out in the summertime and you're working really hard, so you're mowing the lawn, you sweat a lot, you're going to need a lot of water. You're going to need more water than you would sitting in the house in air conditioning playing video games, right? So there's a difference in a way that our bodies react and work. If we're not putting water in, the water can't come out to cool us, to clean us, to make our bodies work and function properly. So how much water should you drink a day?
8 glasses.
2 times.
8 glasses? 8 glasses? How,
A gallon.
3 liters.
gallon? Gallon a day? I hear a gallon. Anybody else? Is that enough? Too much? Can you drink too much water?
Yeah. You can drown yourself, can't you?
Yeah. You can get sick from drinking too much water. Some people have. There's been a case where a lady was trying to win some free tickets somewhere, and the contest at the radio station was drink as much water as you can, and she drank like a gallon of water, diluted her electrolytes, and she died. So yeah, you can drink too much, but it's very, very rare that you drink too much water. You know, you go to the water fountain and you drink a little bit, and it's just maybe even half a glass at the most. You think you're drinking a lot, but it's not very much. Okay, so we need lots and lots of water. We need a minimum of 8 8-ounce glasses of water a day. That's the minimum that you should be drinking. If you're active, you drink more. Okay? So keep that in mind. Water is it's the universal solvent. Water is about 68% of living cells. Now, kids are closer to 70-75%. As you get older, you know, grandma and grandpa, they're closer to 40-50% water. That's why they look all wrinkly. Yes?
Why is that? Like, does anything replace the water? Or?
Kids? Why do kids have more water?
Yeah.
Well, a lot of it is just the way their bodies work. You know, their cells are working well, and they drink a lot. All babies do is drink and go to the bathroom. So if they get enough water, if they're getting enough intake, they're going to create enough water inside their system, and they're going to maintain it. They have a little extra layer of fat too that keeps them warm, so that they don't have to worry about losing too much water. So yeah, they are pretty squishy. Yes?
Why can't, babies drink water?
Why can't babies drink water? They can, it's just not beneficial for them. There's no nutrients in it. So they can drink water, but they're not getting anything out of it. Now they say don't let them drink water, but in reality, any type of fluids will keep their blood pressure up and keep things going. If you don't have milk, you could give them water to keep their blood pressure up. Now, will that last them very long? No. They're going to get hungry and cry and scream and all those types of things. But if you give them too much water, it will decrease the electrolytes in their body, and that can be detrimental to them. So they won't die. They won't die. They could, if you give them too much, it can destroy their electrolyte balance, and they could die from that. Yeah. But if you have a little kid, maybe not a real little baby, but you know, right at the time when they're trying to get off bottles, you should never give a baby a bottle in bed, ever, because that increases their hearing problems, it increases their earaches. So you can give babies water in bed like that when they're not using it for sustenance for food. Yep. Never give baby a milk bottle in the bed or a crib. It'll give them earaches every time almost. Something more to think about, right?
But what is that?
Why is that? Was because when they lay on their back and drink the bottle, they prop it up. A lot of times you'll see the parents will put the bottle in there, put a pillow underneath there, and let the baby, they just drain it right down their back, right down their throat. In the back of the throat, there's little tubes called eustachian tubes, and that milk will go up the eustachian tube into the middle ear, and it's like a breeding ground for bacteria. Yes?
So if it, like you're not putting babies in bed, is it still bad if you like put them in like a boppy or something and then prop up the bottle?
Yeah, anytime that they're leaning back and really leaning back almost flat, and it's going right down in through there, you should always hold the baby up and feed them almost upright. But parents get a little bit lazy and busy, and they just stick a bottle in their throat, and that's what causes lots of earaches. And they'll say, oh, I didn't do anything. But that's why. Hold the baby up. You know, when you're nursing, and if you breastfeed, the baby is not laying completely on its back flat. It's sideways. So that won't drain into their ears like that. So the best way is to breastfeed if you can, as long as you can. And then once that's over with, then prop them up so that they can swallow without it going back up into their ears. Okay? Make sense? Perfect. Now you can all have kids. You're all set. Except you guys. You're out of luck. So, water also has high heat capacity, which we talked about. What has more heat in it? A swimming pool or a boiling pot of coffee? Which has more heat capacity?
Swimming pool.
Somebody said swimming pool. So yawn with an answer, I think, maybe. Swimming pool, that's right. There's more heat in a swimming pool than there is in a pot of coffee. Okay? That's why when you live next to the ocean, like San Diego, it's a beautiful. Anybody ever been to San Diego? L.A.? Beautiful place because you're right on the ocean. The ocean maintains the temperature for the land inside and out, and you end up having a beautiful environment. It keeps the heat in that area. It never gets cold. Always beautiful. High heat of evaporation is another thing. It evaporates, it pulls the heat out of your body and cools you as you go along. So water is very important for that. So 60% of the body weight, depending on your age, about 60% is water. Molecules of water are polar so that they react well with other molecules. They are liquid at body temperature. You can have 3 different stages of water. You can have solid, liquid, and gaseous stage, right? It absorbs and holds heat, keeps you warm inside. It dissolves everything like sugar. If you take a sugar cube and put it in your mouth, it's going to dissolve into that fluids inside your body and become part of it. The glucose will dissolve in the fluids in your bloodstream and goes right out through your blood. Blood has 90% of the water in it. It's very fluid, very liquid. If you get dehydrated, that percentage of water decreases, your blood becomes thick, and it doesn't go through your blood vessels like it should. Water is found inside and outside of our cells. It's everywhere. Everywhere. And it's used for cushioning. It makes your cells kind of puffy. And when you sit on them, then it creates that cushion effect along with your fat, the adipose. But remember, adipose and water do not mix. Fats and water don't mix, right? What happens if you put water and oil together?
The oil rises to the top.
Oil floats, right? Goes to the top. Just like in your sink when you're washing dishes, it goes to the top. You have to get it off there by using some other chemicals. So what's the difference between hydrophilic and hydrophobic?
Isn't it where,
Never mind.
I can do it this way. Let's do it this way. What's the difference between hydrophilic and hydrophobic?
Hydrophilic is water liquid.
Okay.
The other one is like oils that doesn't.
It's like a fear one.
Fear water, right? Give me an example of something that has a hydrophilic and a hydrophobic part to it. Something that is hydrophilic and hydrophobic, all in the same little area. Go back to biology. Do 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 do.
gas?
Well, gas really isn't. Not quite. Something else. Look at something else. We're going to study them in the next semester, next chapter. Go back to biology. 2 layers thick.
Skin,
Skin, but what's the, go back even farther down.
cell wall.
Cell wall, right? Right, you get the hydrophilic and the hydrophobic ends on the plasma membrane. You remember that? Yeah. Okay, so good. Review that a little bit as you go through this, because it allows things to go in and out of the cells, and that's very important. As we go through this semester, you're going to see that those chemicals that have to go through the cells have to be the right chemicals to be allowed to go through, if they're hydrophilic or hydrophobic. So if we have a substance that is in the membrane, one of our phospholipids in the membrane is hydrophobic, what is it going to do to water? Is it going to allow water into the cell, or it's going to keep water out of the cell?
Keep it out.
It's going to keep it out of the cell if it's hydrophobic, right?
That means it's afraid of hydro, right?
It's not afraid of it, it repels it. It's if people are phobic of something, they're afraid of it, they kind of stay away from it, they repel it. Discuss the use of electrolytes in the body and use of acids and bases to maintain homeostasis. All right, so what's electrolyte? Energy? No, energy is a force, basically, like on Star Wars, you know. But what is electrolytes themselves? What are they?
Ions.
Ions, okay? Where do we find electrolytes? Where can we get electrolytes very easily?
Can you get them in
Gatorade,
Gatorade?
Powerade, right?
Pedialyte? Can you get them in juice?
Smart water.
Smart water. Yeah, anywhere that they put those minerals in it, the ions, that's good. That's got electrolytes. Why do we need electrolytes?
Stay healthy.
To stay healthy. What do they do, though? What does electrolyte do for us? That's true. They make us healthy. Help your body move and work. How? It's true.
It energizes the body.
Like the nerve,
Electrical current.
For electrical currents, can be used for electrical currents? Sure. Sodium and chlorine. Sodium and potassium are ions. They use for our impulses or electrical impulses. How else? Give me another example of how electrolytes can help us.
our brain use.
What's that?
Does it help our brain?
Our brain? Yeah. It helps our brain. It's electric up in our brain too. But we get the Gatorade and Powerades and all these things when we drink them, and it gives us these minerals. And the minerals are in our every reaction in our body. Remember the sodium and chlorine, those are electrolytes. So if we mix those together, we get this reaction. But without the sodium and chlorine, we can't have that reaction. It can't take place. So if we're missing an electrolyte, some of the reactions in our body will not work. They won't happen. So we have to have those in our system. We have to drink them, eat them. Okay? So what's the difference between an acid and a base?
Isn't one, what's that scale called? I forgot what it's called, but one's higher and one's lower.
pH scale?
Yeah.
Yeah. pH scale. So we have acids and base. Which was lower? Acid or base on the pH scale?
Acids.
Acid's lower on the pH scale, so that means the base is higher, right? What is neutral? 100? 7? Did I hear somebody say 7? No, that was me. 7? 7 is right in the middle. So the pH scale goes between 1 and what? 14. 7's the middle, that's neutral. And that's what we want to look at. We want to stay pretty close to that 7 numbers because that's part of our homeostasis. Okay? It keeps us in homeostasis. But electrolytes are ions, just like we talked about, and they have the ability to enter into reactions and to create reactions in our system. Without this, we don't work. Sodium, potassium, chlorine, iodine, all these are ions, and they make everything work. So we have to have them. Now, acids and bases are electrolytes. Both of them are electrolytes. They have positive charges and negative charges. They're just like ions, right? If you put a positive hydrogen and a negative OH together, you get what? H plus an OH will give us what? H2O, and that is water, right? So if we take an acid, which is a positive, and we put it together with a base, which is OH, we get water. We can also take hydrochloric acid, which is something that we have in our stomach, and we can dissociate that into hydrogen and chlorine. Or we can take the chlorine molecule that we get from sodium chloride and put that together with hydrogen, and we get hydrochloric acid. The hydrochloric acid, in turn, just helps to break down our proteins, and we can get our amino acids from that. Because we need these electrolytes to make this work. So bases are proton acceptors. They like to take on protons. So they'll take up hydrogens from a solution. And hydrogens will make the solution acidic. So if you take an acid and a base and you mix them together, you can neutralize them out to be water. So if I take a really strong hydrochloric acid and mix it with a strong base, theoretically, you should be able to drink it if there's no other really junky chemicals in it, right? You neutralize it. You have to be very careful if you do that, and I would not recommend doing that unless you know what you're doing, because it can kill you. So we call them acids or alkaline solutions, hydrogens and hydroxy ions. Hydrogen ions make acids, hydroxy ions make bases. We mix them together and we get this situation. Neutral solutions are a solution where we have the same amount of hydrogen and the same amount of hydroxy ions that gives us a neutral solution, or a pH of about 7. 7 is our normal solution. Now if you'll talk to Mr. Lang, this is just the beginning of this. There's a lot more to acids and bases than what we're talking about in this class. So I highly recommend that you go to his classes and find out more about it if you want to talk about this. Okay. So the pH scale is 7. pH is 0 to 7 and 7 to 14. So if it's 7 right on 7, it's neutral. If it's 7.01, it would be what? Acid or base? A base. If it's 6.999, it's acidic, right? And it's, as you go through these numbers, it goes up exponentially. So if you have a pH of 6, it's much more acidic than 6.5. It just keeps going up. Kind of like an earthquake. If you have an earthquake of 9 on a Richter scale, that's a really big earthquake. Much stronger than if it was a 6.0. I talked about that one already. All right, so what is this important for us? Well, the reason we need to know this is because we have to keep our body in homeostasis. If we get out of the pH in our bodies, in the blood or in the cells, we can die from it. If your blood becomes lower than 7.35 or higher than 7.45, you can die from pH poisoning or pH from too acidic or too basic body. Now, we have mechanisms in our system to alleviate this. We have the kidneys, the lungs, we have buffering systems to make sure that we keep this in check. We have to keep in that range, 7.35 to 7.45. We like it about 7.4. That's where we like it the best. But if you eat a lot of meat, you're going to dip down into closer to 7.35. If you eat lots of vegetables, you're going to go up closer to the 7.45. Makes it important. Right? This is a pH scale. Some interesting things on it. Some things that you may not know that have even an acid to it. So right here in the middle we have pH of 7. This is our neutral, pure water. As we go up, this is our bases, this is our acids. So let's go through some of these. Baking soda, seawater, it's about an 8. Toothpaste, it's about a 9, a little over 9. So why is toothpaste basic? Is there a reason for that?
It's got cleaning
It's
substances.
got cleaning substances, and the cleaning substances kill bacteria. So if you get something, bacteria like to live in about the same pH that we do. If you put them in a basic or an acidic environment, they will die. So what we do is we take a little bit of bases and put it in our toothpaste, we brush our teeth, and it kills the bacteria that's in our teeth. It helps to protect us. We also put fluorine in there and some other chemicals that assist that too. Milk of magnesia, milk of magnesium, I guess in there, but milk of magnesia is what you drink when you go to the hospital, and make sure that you have to go to the bathroom. This will flush you out. It irritates your gut, and it's basic of about 10. Ammonia, the stuff that you clean up oil with, that's 11. Soapy water that you wash your hands with is 12. You know, you always see this antibacterial soap. You don't have to buy antibacterial soap. It's all antibacterial. It's all basic. It'll kill it just like anything else. Bleach, very, 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 it's getting very basic. Dangerous stuff. Don't spill it on you. Don't drink it. Don't get in your eyes because it will burn and kill the cells. And then the last one is oven cleaner or drain cleaner. You know, so many people will dump drain cleaner down their drains and they can't get the drain to open up, so then they call a plumber. Plumber comes in, plunges it, acid all over it, or base all over it. Burns him. So you have to be careful of that. Going the other way, urine is 6, milk is about 6.6. Now as you see, every time we go down one of these levels, it gets 10 times more potent, stronger. 5 is acid rain, coffee. Tomato juice is 4. Grapefruit juice, orange juice, and soda pop. Soda pop's about 3.5, 3.4. So if you drink lots of pop, does anybody drink a lot of pop in here? Popaholics? Soda popaholics? Nope. Okay, good. Lemon juice, 2 to 3. Vinegar is 2.9. Vinegar is really cool because you can set that on a shelf and it won't spoil. It has so much acid in it that hardly anything will even live in it. Right? Lemon juice is really good for your body because it goes in your system and it helps to cleanse your system, and people use it for fasts. You go on a 7-day fast, you drink lemon water, and it helps cleanse your body as you're doing it. Stomach acid, 1.5. Very, very acidic. If you put stomach acid on your hand, it will burn through your hand. It'll burn in your hand. Okay. Then we have battery acid. Very powerful stuff. If you're going to jump a battery to get your battery started, you put the cables on and then you back away, long ways away. Because if that battery blows up, you're going to be toast. You look like Daredevil on that movie. All wrinkly and torn up. Right? And you cannot stop it. If you take hydrofluoric acid, it converts, and that's very deadly too. Hydrogen and fluoride together, it will kill you. All right. And this is how you test your pH. You take this, these measurements, and you will test your pH, and it tells you exactly what the inside of your body is like, if it's too acidic or too basic. We also use buffers. Buffering systems is basically we take an acid that's in our system, and where we get our acid is from when we breathe. When you breathe in and out, you're expelling carbon dioxide, right? Everybody know that? Where do we get our carbon dioxide from to breathe out? Where does it come from? Inside the body? But where specifically? What process makes carbon dioxide? It has 3 phases. Three phases. This is from biology. You should have had this, a big unit on this. Everybody freaked out. It's 3 phases, 3 stages. Glycolysis. Right? Does everybody remember that? Somebody say something. Nobody remembers glycolysis? Krebs cycle, citric acid cycle?
I don't think we went over it.
You never went over that in biology? Here? Did you have biology here?
No, I
Where-
took it sophomore year.
Yeah.
Say,
Wow. So where'd you have biology at? High school?
Me?
Yeah.
Yeah.
Yeah. How many people had biology in high school? Have you had it since then or just in high school?
that's
Had it
not
here too.
You had it here too? Okay, so you should know this. Can't let you off the hook, buddy. All right, so go back to your brain cells. Cellular respiration. Tell me what now. Tell me what's going on. And those of you that had biology here, help him out. What's the byproduct of cellular respiration?
Carbon dioxide.
There you go. That's easy. What else? 3-letter word. ATP. What else? Starts with an H, ends with an O, and has a 2 in the middle. Water, right? So those are some things we get from breaking down what molecule? Nope. Oxygen's there for, helps it out, but what are we breaking down? What big molecule are we breaking down? Glucose, yay! So, we got a glucose molecule, we break it down with the end, we go through all the steps, all those cycles, and we end up with carbon dioxide, water, and ATP. Right? Does that sound familiar to anybody? No. How many people again had biology here? 1, 2, 3, 4. The rest of you had it in high school, huh? Interesting. Okay, so we have buffers. How did we get that far? I don't remember. So we want to keep ourselves in homeostasis, and to do that we have to have buffers. What's the difference between organic and inorganic? Everybody had chemistry, right? So if it's not living, it's inorganic, but if it's living, it's organic?
Yeah.
What delineates specifically the organic versus inorganic substance?
Organic is like
Carbon. Somebody said carbon. Yay, carbon. Carbon's really important. It helps us. It's what we are. We're carbon-based molecules, or organisms. Carbon has the ability to bind with 4 separate elements, right? So if it has carbon in it, it is a organic substance. So I go down here to Hy-Vee, and a big sign says organic bananas. Right next to them are bananas. What's the difference? Nothing?
The only difference would be they're not treated with pesticides.
The only, perfect. The only difference is they're treated differently as far as pesticides, herbicides, chemicals, treatments. So that sign should say chemical-free versus organic. Organic is everything. Everything you eat is organic, right? If it comes from, if it has carbon in it, it's organic. That chair, that bench that's full of wood, that's organic. It's made in a tree. Trees are made with organic, right? You're not going to eat that, but you could. Kind of tough and not tasty, but that's what it works. So don't buy into that. If it's organic, every food is this organic, but it has to be chemical free. That's the better way of putting it. Okay? And natural doesn't do it either. If they put a sign up that says natural, well, it's all nature, comes from nature. So it's,
Wait, so organic means, chemical free?
Yes.
according to them, yes. But organic, as far as chemistry goes, all foods are organic. Because they have a carbon in them. Okay, so inorganic things are water, salts, sodium chloride. They don't contain carbon. Inorganic things like rocks are non-living. Most things are non-living. Organic things have carbon in them. Carbon is fairly rare in the earth. About 0.03% of the earth's crust is carbon. But every time that you, like coal and oil, is all carbon-based molecules. They come from dead plants and animals, and we continually recycling those. 18% of our body weight is carbon, and it's the most stable when we combine it with other molecules. So 4 categories of carbon compounds that we have carbohydrates, lipids, proteins, and nucleotides or nucleic acids. Give me an example of a carbohydrate.
Broccoli.
Broccoli, okay, good. What else?
Bread.
Bread, yep, bread's a good one. Rice, right? How about lipids? Give me an example of a lipid.
Olive oil.
Olive oil? Popeye? No, that's a cartoon. What else? Give me another example of a lipid. Or give me an example of a food that has lots of lipid in it, maybe. Meat's got it, especially if it's a fatty meat. Butter, right?
Milk.
Bacon. That's good. Bacon. Protein, right? Give me an example of protein.
Steak.
Nuts.
Steak. Yay, steak. What else?
Nuts.
Nuts have got protein, yes.
Shrimp.
Chicken, shrimp. Anybody getting hungry yet?
Yes. I've been hungry all period.
Been hungry all period? Well, we'll be done here shortly, I promise. How about nucleotides? Where do we find nucleotides and nucleic acids? Juice, maybe? But where do we get the, remember in biology, where do those nucleotides come from? What do we use nucleotides to make? It's found in the middle of the cell. It's got a membrane around it. The nucleus, right? What's inside the nucleus?
The cell.
DNA, right? DNA is made up of nucleotides. So everything that is living, everything that has DNA has nucleotides in it. So when you eat that piece of chicken, it was alive, it has cells, it has DNA in it. So you chomp up the nucleic acids and nucleotides, and you can use those to make your own DNA to replicate your cells. Pretty awesome, right?
So we could like make clones and stuff?
Not quite, but we're getting there.
So like nucleotides or anything that was living.
Everything that was living or is living has nucleotides in it. As long as it has DNA, it will have nucleotides. So organic, we talked about that. Anything that has carbon in it except for carbon dioxide and carbon monoxide. What does carbon monoxide come from? Where do we get that?
Burning of fuel.
Burning of fuels, as in your car, right? So if you park your car in your garage, it's going to give you carbon monoxide. If you sit in it, it's not a good thing. You can't smell it, you can't taste it, but it will kill you. So, let's talk about carbohydrates when we come back on Wednesday. Okay? So finish up reading this chapter. Make sure you get your post-tests done. Start working on those too, and then we'll go on.